All right, in this chapter, we're going to take everything that we learned about finding derivatives of a function and just kind of stand it on its head. We're going to try to go backwards. So as a quick introductory example, suppose we know that the derivative of some function is equal to 6x squared, and we want to know what is that original function. We might, maybe guess a few, stumble around a bit before we come to the conclusion that our function must look something like 2x cubed. And if we call this function little f of x, if we call the original function, right, that's 6x squared little f of x, there's a convention that says use the same letter but capital letter to denote this new function. So here I called it y, but we might say big F of x is 2x cubed. We call this an antiderivative of the function 6x squared. And I should be careful to say that it is an antiderivative, not necessarily the antiderivative. We could find an antiderivative for lots of functions. For example, the function f of v is equal to v squared plus 2v. So I want to find a function whose derivative is equal to v squared plus 2v. Now when we take derivatives, we can take derivatives term-wise, split it up over addition. So we're going to just undo that process one term at a time. So big F of v, the function that I would have to take a derivative of to get v squared would be 1/3 v cubed, and the function that I would, or the term I'd have to differentiate to get 2v would have to look like v squared. So there's an antiderivative of that function. This next one, you'll note we have this radical in it. We also have stuff in the denominator. Now, if we were taking the derivative, we would first put it in like a power rule friendly form, and that's how we're going to start here. So I'm just going to rewrite the function first. This is still little f of x, so I've got x to the 1/2 minus 2x to the negative third power. So when I'm looking for an antiderivative, big F of x, a function whose derivative is equal to x to the 1/2. Now you might have already kind of come to this conclusion or observe this pattern, but if I take a derivative and I get a 1/2 power, then the power that I must have started with has to be one more than that, right? When we take the derivative, we subtract 1 from the exponent. So if we're going to undo that, we're going to add 1 to the exponent, so we get 3/2. And now if I take this derivative of this term, I'd have to bring that 3/2 down. So I'd have a coefficient of 3/2 when I really want a coefficient of 1. So to make this all work out, I'm going to add a coefficient of 2/3 in front. That way when I bring the 3/2 down, it'll cancel with the 2/3 that are already there. And now we're going to go to the next term. I'm bringing down the constant factor because we get to bring down constant factors when we differentiate. So when I'm undoing that process, I'm going to do the same thing. Now I get to just focus on this x to the negative third power. So I'm going to add 1 to the exponent. Adding 1 to negative 3 gives us negative 2. And if I bring down that negative 2, I want to get just to x to the negative 3, so I'm going to add a factor of negative 1/2. Now if I bring down the negative 2, it cancels with the negative 1/2. We're left with that factor of negative 2 in front. And if we clean this up a little bit, we have 2/3 x to the 3/2 plus x to the negative 2. So when we're finding antiderivatives, we're doing a couple of things. We're undoing that power rule overall, but that means we have to do two things. That means we're going to add 1 to the exponent, but then we also have to figure out, what's this coefficient in front to make sure that I end up with the desired coefficient after I take the derivative. And that basically, you can sum up summarize that rule that we're using here to say that if I want an antiderivative, I'm going to add 1 to the exponent and then divide by the new exponent. As long as we've made sure that we've brought down any like coefficients that already appeared. Then dividing by that new exponent will result in the right function that we're looking for. This next function looks a little bit more complicated. We've got a couple of factors. Now, when we take the derivative of a function, we cannot just multiply. When we take the derivative of a product, we have a whole special product rule, right? We end up adding a couple of things, and we don't just multiply derivatives of terms. So when we find an antiderivative, we can't just find an antiderivative of each of these factors and then multiply them. I want to see this function as they've given it to me as the derivative of some other function. And one of the most helpful things to realize is that this part here, the 3x squared, that is actually equal to the derivative of what's inside those parentheses. And that means that this factor of 3x squared, when we took the derivative to get this function f of x, that factor of 3x squared probably came about by using the chain rule. So if you just take a look here, I'm gonna just kind of cut to the chase and give you the result, and then we'll do a check so we can see for sure that we're right. An antiderivative for this function is x cubed minus 1 to the 3rd power. Now, when we check this, right, big F of x, x cubed minus 1 to the 3rd. So when I find its derivative, we're hoping we should get the function they gave us. So we bring the 3 down, then we have x cubed minus 1 squared, and then the chain rule says times 3x squared. And that is, in fact, equal to the function they gave us. So as we're finding antiderivatives, one of the things we want to be on the lookout for is, was the chain rule used? And a big part of that is seeing that, this piece that I see here happens to be the derivative of this other piece that shows up. All right, let's try another one. Now here we have another some stuff raised to a power. If I took a derivative and I got some stuff raised to a power, chances are pretty good that an antiderivative is going to be that same stuff, in this case 2x plus 1, raised to a power. I just need to add 1 to the exponent. So one of the things we kind of realize pretty quickly in this process as we're learning to take antiderivatives is that we don't always come across the right answer the first time. So here's my first guess as I'm working through this, is that I want this same stuff. I got to add 1 to the exponent, so that'd be 3/2. And then I'm going to do a check and see where that leaves us. So big F of x is 2x plus 1 to the 3/2. Then its derivative, big F prime, is 3/2 times 2x plus 1 to the 1/2 times 2. And we can do a little simplifying here, a little canceling, and we get 3 times 2x plus 1 to the 1/2. Now, this obviously is not the original function. It's not equal to the original function. So this, our first guess is not correct. But we are off by a factor of 3, right? We're off by a factor of 3. So even though this is not right, and that's not an antiderivative that we're looking for, what I want, so for my second guess, I want to compensate for that factor of 3 that we'll have, right? And the way I can compensate is just to add a factor of its reciprocal out front. I'm going to add a factor of 1/3 to my first guess. So instead of just 2x plus 1 to the 3 halves, I'm going to have 1/3 times 2x plus 1 to the 3 halves power. Now, if I check, one-third times, this would be 3 halves, 2x plus 1 to the 1/2 power, and then times 2. Now, look what happens. So the 2 still cancels there, but now the 3 cancels with the 1/3, and we have 2x plus 1 to the 1/2, and that works. That is the function they gave us. So to recap here, an antiderivative of a function is a function whose derivative is equal to that given function, right? Is a new function whose derivative is equal to that new function. We're trying to undo this process. And in this sort of brief introduction, I think we've already learned that undoing the derivative process is maybe a little bit more involved than just finding the derivative. Just reversing the order of things is a little bit harder. We're going to be kind of patient with ourselves. We're going to allow ourselves to maybe need to take 2, maybe 3 tries before we find an antiderivative sometimes, and that's okay. That's sort of the way of it. We're going to do some more of this in the next section.